Okay, well, welcome everyone, and thank you so much for attending our monthly College of Natural Sciences webinar. My name is Allison Sherwood. I'm the Interim Associate Dean for the college. Through our Pilina webinar series, we're aiming to reach the broader audience and the broader community and share with the world all the wonderful research that happens both in the College of Natural Sciences and across the Manoa campus. Today's webinar features Dr. Jeff Kuhn of the Institute for Astronomy here on the UHM campus. Jeff received his PhD in physics from Princeton University in 1981. Over the years, he's worked as a professor at Princeton and Michigan State University, and as an astronomer at the National Solar Observatory. Since coming to UH about 25 years ago, he's been a professor at the Institute for Astronomy and was the director of the IFA Maui Advanced Technology Research Center for a decade. He's worked to develop new concepts for optical and infrared instruments and unusual telescopes, like the Daniel K. Inouye telescope on Haleakala and other large optical systems. Most recently, he's helping to build an unusual telescope in the Canary Islands that will advance our ability to find evidence of life on planets around other stars. And so now I'd like to turn our time over to Dr. Kuhn for his presentation, Are We Alone in the Universe? Astronomy may answer this question. Welcome, Jeff.
Thanks, Allison, and thanks for the invitation to talk. You know, some of us, we just love to talk, and I'll take every opportunity, and this is great. Unfortunately, it's remote, and so I'm not sure how these have gone in the past, but please, I encourage you as we get into this to raise your hand. Hopefully, Allison and I will see your interest, and I'd like to try to be as interactive as we can as we go. So as Allison described, I'm an astronomer. Actually, my background is in physics. I did take one or two astronomy courses in graduate school, but mostly it was physics. Most of my few years have been spent working to develop instruments and in particular telescopes. So today what I want to do is I want to introduce you to some telescope ideas. And the general interest here is that most of our perspective, I think, on life and the universe derives from what we can do with our telescopes. And as we change their capabilities and as they evolve, it makes quite a difference in how we see the universe. So a few weeks ago, I was in a small village not far from Bremen. And I was amazed to learn that the world's second largest telescope was in this little village of about 10,000 people. And they're very proud of it. This is a historical photograph of the telescope, which doesn't look like much to our eyes, but in fact was instrumental in solving one of the early planet search problems. Now, back in the 1700s, it wasn't planets around other stars, but it was planets around our star that we were looking for. And this telescope was built to look for the missing planet between Mars and Jupiter that turned out to be not a planet, but asteroids, and it was instrumental in doing that. So our vision of the solar system changed quite a bit in response to this little telescope. It was only 50 centimeters. The village is rightfully very proud of their place in the history of telescope technology. On the right-hand side of the image is a picture of the telescope as it has been restored, very much like it was back in the 1700s. So I'm gonna jump into some details. I want to tell you a story about how technology and telescopes have evolved and where some of us think they're going over the next 10 or 20 years that may change our vision of the universe in a significant way. So this is the future. We're part of a group that has been hired to look at the design of what might be the next generation optical telescope that could be tens and hundreds of meters in size through a segmented telescope that we'll talk more about in a little minute. But this is the kind of vision of where the technology that we're talking about today will take us, and I want to explain to you why that's so important. So first, some ideas about telescopes. So you know that the telescopes we use, basically they collect light and they concentrate the energy onto a detector. So detector can see an otherwise invisible object to the naked eye. Here's an image that you might get from a telescope. That light comes in from the right, it reflects off a mirror, and then it's focused, or the energy is concentrated on a detector, and that's the image that we get. Now, there are properties of light that are important to know about, and one of them is that even though it looks like all the energy is focused to a spot, if we amplify what we call the intensity scale here, so that's a scale which we say is linear. It just, so bright is white, and dark is less intensity. If you could see the faint energy that's in that image, you'd find out that actually it occurs in rings, and that energy isn't coming to a single spot. It's coming to rings of energy that we call airy rings, after a physicist in the 1700s who was instrumental in explaining some of these properties. So how do you make energy come to a more concentrated spot so that it's not obscured by intervening other noise sources? And the answer is you make the mirror bigger. If you had a mirror that was 10 times larger, this same image would look like this. And if we expanded the scale so we could see the faint parts of it, you would see that it's still much more concentrated than this. And so one of the main reasons for building bigger and bigger telescopes is to be able to see fainter objects, but also to concentrate the light more selectively in these objects. The effect of a mirror, which is what we're going to be talking about, is to produce that image. And so I don't know if you can see my crosshair, but in the small boxes in the lower left is a picture of what also happens to an image because of the atmosphere. And the atmosphere will also spread out the light in a complicated way. And as the turbulence in the atmosphere gets worse, the light gets spread out, so you don't even see in the two images on the right, two panels below, you see that it gets spread out so much that you can't even see that the star is there. So these are all problems that a telescope has to solve. Concentrating the energy so that we can see faint things is the basic story of the day. A distorted mirror also, if the mirror doesn't have a perfect shape, and we'll describe what that means, the light also ends up looking like what the atmosphere does to it. We can't hardly see that there's a star there. So that's what telescopes do. It's kind of interesting to look at how technology has affected the kind of energy concentrating telescopes over the years that we can build. You probably know that the first time an energy concentrating telescope was turned to the sky with, at least with recorded results, was at the time of Galileo, the 1600s. His was a telescope that was based on lenses, and it wasn't very big, not much bigger than our eyeball, in fact. It was, I think, Mersenne, a French scientist, not too many years later, who said, well, it would be great if we could make reflecting telescopes that didn't use lens optics. Lens optics absorb some of the energy, and they're heavy, and they have lots of glass to them. If we could just make a reflecting surface, we could do a lot better. And it was Newton towards the end of the 1600s who really created the first reflecting telescope that we know about. It wasn't like a telescope we see today. We didn't know at the time that glass could be made into a reflecting mirror, but it was made of a metal surface that was called speculum. Speculum was mostly an alloy of copper at the time. But what Newton did show was that if you could shape the surface of the glass very accurately to a millionth of an inch, that you could create an energy concentration that allowed you to see faint things in the sky, just like Galileo's telescope, if you could make the shape of the mirror accurate enough. I'm not going to go through this whole list, but there were some other really important technology achievements over the years. One of them was by Mitchell, who in the late 1700s showed that if you made the mirror not a spherical surface, but a parabolic shape, that it had a much better focus, and the energy was focused to a much more highly degree. The real advance in making telescopes that look like telescopes we see today was Foucault, and a Swiss engineer by the name of Secretan, who was able to show that you could silver glass, and theirs was a chemical technique. And once you silvered glass, you could achieve a reflectivity that was much better, in fact, than even the metal mirrors that were speculum beforehand. Foucault also was really the first to show that you could test his mirrors in the process of polishing them, not just by looking at an object, but by doing optical testing. And he was the first to show that there were systematic ways of creating a very, in his case, parabolic shape that concentrated energy in a way very similar to modern telescopes. In recent days, historical times that we know about, the Hale telescope or the Hooker telescope, George Ellery Hale was a solar physicist who had the leadership role in California to produce the Hooker, which was very important. It changed our vision of the universe and seeing galaxies and nebulae. Of course, it was glass. The Palomar telescope was the first time we had low expansion glass because thermal expansion was a problem, and that also was instigated by Hale. And then in modern times, in the 1990s, we had the first hint of building even bigger telescopes that were made from segments of glass, and they were using materials even more sophisticated than Pyrex. Okay, so there's a 400-year history that is tightly coupled to some real big advances in our vision of the universe, starting with the planets around the sun and the missing planets, to the discovery of galaxies and the expansion of the universe, that were all tied to the technology that each one of these jumps in optical energy concentrators enabled. All of them, though, depended on shaping glass, and I want to pay some particular attention to why that's so important. And it's because we have to shape the glass if it's going to concentrate the energy, like I showed in that first slide. Effectively, the shape has to be accurate to a fraction of a wavelength of light, and that number is much less than a millionth of a meter. The approach that Newton described is really the same one that we're now using 400 years later, which is to put an abrasive material, in this case on glass, not speculum, and to rub it. And if we rub two pieces of glass together, we'll make a spherical surface. The slide on the bottom shows this in a more sophisticated form where we have computers to do the rubbing. And what you're seeing is the James Webb, one of the mirror segments for James Webb, being computer polished. Those weren't glass, of course. Those were beryllium metal for other reasons. And we have developed other techniques. The image on the right shows how we shape very accurately glass by putting the glass in a vacuum and focusing a very highly energetic beam of ions onto the glass. And what it does is that ion beam ablates the glass and just blows away some of the material. But basically, it's again this idea of removing material to shape the glass. And our technology and our understanding of the universe is dependent on this since the time of Newton. Our future is, as we started to say, dependent on being able to build bigger and bigger optical systems that can concentrate the energy more effectively. And so I put together a set of slides of future telescopes that in fact, one of them is not future now. This is the James Webb telescope on the right that represent the trajectory of modern astronomy to larger and larger diameter telescopes. And two of them are expected to be in space. Why do we send telescopes to space? Well, in the old days, we sent telescopes to space because we didn't have the ability to correct for the distorting effects of the atmosphere on the light as it passed through the atmosphere. That's not so much the reason anymore. Now reasons have to do with avoiding the absorption of the Earth's atmosphere due to, for example, the molecules of gas in our atmosphere absorb big parts of the infrared, in particular longer wavelengths. And so the James Webb Space Telescope is particularly powerful because it looks into the infrared and it's above the absorbing influence of the atmosphere. If we can affect and correct for what the atmosphere does, we can solve for the problem of what we call atmospheric distortion, and we'll get to that in just a second. There is a larger telescope, and it's worth noting. This is the Green Bank telescope. It's 100 meters across, and it's a very attractive telescope, in my opinion, because it doesn't have a hole in the middle of it. It's called an off-axis telescope, and the light comes in, bounces off of the subreflector, and then back off to the side where the detector systems are. This is a telescope which we'd love to be able to build as an optical instrument, and I'm going to talk to you about how we think we can build optical telescopes that large. Because it works in the radio, it works down to wavelengths of light energy that are have typically millimeters at the shortest wavelength. Its surface doesn't have to be so precise. And this is the other problem of technology in building telescopes as we go forward, is that gravity is a horrible problem when we have to change the pointing direction of the telescope, because that means that the gravity vector, the effect of gravity distortion, changes the shape. We could build a shape that corrects for the gravity for a particular angle, but because it's on the ground, it has to track. And as it tracks, the distortion changes. And that's the other part of the technology problem in moving forward with big telescopes. All right, so that's a summary of telescopes and where they are and some of the ingredients of the problems to make them work. This is kind of an interesting figure that shows our evolution towards larger telescopes. And it's just a bird's eye view of what the mirrors look like. The 30-meter telescope that might someday be built, it's struggling. If you looked at all the mirror segments, looking down on it, looks something like this. The Europeans are building a larger telescope called the EELT, and that has a diameter of about 40 meters. There is a group building a telescope in the southern hemisphere called the Giant Magellan Telescope, which is a very different design, where the mirror segments are as large as possible. We might wonder why that is. Why are each of these telescopes so very different? For comparison, the size of a tennis court is down here, and so the EELT is approaching the size of that big radio telescope, but it's not quite there. What I and a group of physicists and scientists have been working on for a few years is a telescope which is in diameter bigger than the 30-meter telescope, with we call those, each one of those mirrors is a subaperture, with subapertures that are as large as we could practically make them, given the technology I'm going to tell you about. And this is called the Exo Life Finder telescope. Okay. Okay, so here's the problem with gravity again. If you want to make a big telescope, you want to make it as light as we possibly can. And to make it as light as we possibly can, we want to make the mirror as thin as we can. But eventually the mirror is distorted by gravity. And so this is just a slide that describes what the relationship is between the distortion in a piece of glass that's supported from behind. So we're going to be talking about optics that involve glass as a reflecting surface, and then a truss structure that provides more stiffness. The problem is that glass, eventually you'd like to make it as thin as you can, but when it does, then it distorts due to gravity, and as it tracks in the sky, that distortion changes. So this is our technical issue with materials. It's really an engineering material problem. If you find stiffer materials, then the distortion gets smaller. But often the stiffer materials are more massive. And what matters in understanding how you'd make a telescope is the stiffness to the density of the material. And it turns out that glass and steel have about the same. It might surprise you that glass is as good a building material as steel is. And it is, except for the fact that it has a critical stress that it catastrophically fails on us in general. But when you look up at those glass and steel buildings, recognize that the glass has a structural element which is just as significant as the steel. in most cases. Okay, so mirrors consist of a piece of glass and a background. The evolution in mirrors in historical trends has been from thick pieces of glass. So over here on the left is a mirror that is a typical mirror built in the 50s and the 60s, and that mirror is thick in order to be stiff so that gravity doesn't distort it. We've realized that we can decrease the total mass of a mirror by mating steel and glass together, and that decreases the total mass. And the Keck telescope, this is the back of the Keck telescope, and you see that the mirrors are these surfaces, and they're really quite thin. And then there's this elaborate truss structure in the back that allows the Keck mirror to be an order of magnitude less massive per square meter than mirrors that are older than that. Lots of technology has gone into building mirrors, but also technology into creating the mechanism that the mirror is a payload for. So you want to think about a telescope as a large structure of optics, which is a payload on a very accurate and sensitive mechanism that points it with the accuracy of better than a clock at locations in the sky where we can collect the information that tells us our vision of the universe. I just wanted to point out that with the Palomar telescope, there was a very important mechanical invention called a Fourier truss, which allowed the structure to be built in such a way that the distortions were compensated. So there's a lot of cleverness that has already gone into telescope design to create these beautiful machines that are very, very accurate. Okay, so 400 years of telescopes. We've gone from two mirror speculum reflectors to segmented mirrors that give much lower mass and larger primaries, better thermal immunity, and lots of other mechanical advantages. Lots has happened in 400 years, but in many ways, the shaping of the glass and also in some ways the mechanical structures are still very much descendants of the thoughts of Newton 400 years ago on how we shape glass. So now I want to remind you, you've probably heard this before, that in your lifetime, astronomy has changed enormously. Now, my primary astronomical research is mostly related to the sun, but I have been quite amazed in my days. As a graduate student at Princeton, I had some very well-established astronomers say that we didn't really think that there were planets around other stars. The conditions to make planets around other stars was quite difficult. And so Martin Schwarzschild and Lyman Spitzer, who were well-established astronomers then, we're not really looking towards the kind of astronomical world that we now live in. So you should know that when you look up at the sky, there are more planets than there are stars likely. It's just that we haven't been able to see those planets. Our understanding and perception of the universe changed enormously about 25 or 30 years ago when our technology allowed us to find the first evidence of a planet orbiting around another star. And this is just a slide to show that now we know that most stars have planets, and a very significant fraction of them probably also have planets that have water on them, even liquid water. And this is the plot that shows the distribution based on our technology, not necessarily based on the truth for knowing how many Jupiter-like planets versus rocky planets there are, but that this is an area of active research, which is really defined by our vision of what our telescopes can do. So we're in this special time where we can now start thinking about what biology on very different worlds would look like. And one of the common arguments I have with my biologist friends is whether or not life is common in the universe. or is life rare? Well, now I hearken back to the discussion that I mentioned in my graduate days, where we were pretty much told that planets around other stars are unlikely. And of course, now we know with our new technology, our vision of that universe has changed a lot. Biologists that I know will tell me that, well, the conditions to create life are extremely rare, and that it seems unlikely that life could exist anywhere else on the universe. That Earth is special. I'm not a biologist by trade, but I have watched as our vision has limited our imagination. And I think that it is interesting that if you look at where we are in the Milky Way, imagine this is a picture of a galaxy not very different than the Milky Way. The very nearest star to us, Alpha Centauri, which is a triple star system, just a few years ago, we discovered that one of its three stars, not a sun-like star, but nevertheless a star, not too different in mass compared to the sun, has a planet, and that planet likely has water on it. So this exoplanet that we found now on the first available space closest to the sun, as we look outward, is probably a good lesson to all of us, to suggest that life may not be rare at all, and that Earth may not be special at all. And I want to take that theme a little bit further and point to some interesting papers and ideas that you may not have seen. But again, this is in the context of the moral of this story, which is our understanding of the universe, and even life on the Earth has been defined by our limited vision and what we can do with our telescopes. So I don't know how impressed you were by this fact, but when we did have the capability of seeing fast-moving, not very bright objects passing near to the Earth, it wasn't long before we found Oumuamua. Oumuamua, we know its velocity, we know how it moves, and there is no doubt that it didn't originate from the solar system, and it didn't pass so far away from the Earth. So what do you think about the idea that the solar system is actually part of a cosmic web of interacting stars and possibly planets? Well, you should know the name Crick, of Watson and Crick. Crick was a very clever scientist. He had many broad-ranging ideas. This is a paper from 1972, where he argued, apparently not to very many people that believed him, that if we looked at a timeline where here we are in the present, and this is the age of the universe, which at the time, fairly recently, we knew to be almost 15 billion years based on the microwave background. And what Crick said was, well, based on his understanding of the complexity of the DNA molecule, that he didn't really see how it was possible that there was enough time to develop life in just the age of the Earth. And in fact, not even the age of the Earth. The age of the Earth is about 5 billion years old, but the time since there were oceans is even less than that. And so he argued that we are part of some larger network, and that life probably originated elsewhere, and it came to the Earth, and he called that panspermia. He called it directed panspermia because he thought that there was some sort of cosmic logic to how it was happening, but that's probably another argument. Now, you've heard probably this idea that complexity begets complexity, and that the rate of change of the measurement of anything complex is proportional to how much complexity is there that you start with. This is called Moore's law. Moore was one of the first to show that argue that if you looked at, say, the amount of information that we store on the Earth, or the amount of information we store on an electronic device the size of your hand, that amount of information is growing at what's called an exponential rate. It means that there's a at doubling time. And the doubling time for Moore's law and digital information is about 2 or 3 years. Now, if you follow this trend back, it takes you back to not quite the time of the Gutenberg Bible, but the ability to print books. But it is a remarkable observation empirically that information, however we measure it, tends to be an exponential process, that it doubles over a fixed doubling time, over many doubling times. Well, a few years ago, a biologist and a mathematician, Sharav and Gordon, argued that, well, we can measure the complexity of life by measuring how any given species transfers to its offspring the information that makes their lives survivable. So for most living species, it's the DNA that we pass on to our offspring, which provides whatever they need to be able to survive. And many of the species that we know about, fish or worms or cyanobacteria, have been around for a very long time. The oldest life I think we know about is cyanobacteria. And we can sequence their current DNA, and we know when they emerged in the archaeological record. And if there's another step in this argument, but if we have a mechanism for filtering out in that DNA sequence, that by sequence I mean the number of base pairs, if we count the number of base pairs in the DNA, so for us, if we stretch out our DNA, it's a couple of meters in length. If we took a DNA molecule of a human, and it's got 20 billion base pairs roughly. That's the information content. That's like the number of digits in a cell phone that we could measure to talk about doubling time. And so what they argued was that if you started with prokaryotes and eukaryotes and worms and fish and cats and dogs, that the doubling time for the number of useful DNA base pairs is a few million years. Now, our archaeological record, so this is present, and this is the birth, the origin of the Earth. What we see is that, well, if we wanted to extrapolate this back to, say, the origin of life, if we think it happens when there are just a few base pairs, that it's 9 or 10 billion years ago. The Earth is only 4.5 or 6 or 7 billion years. This seems to be the part of the statistical argument that Crick would have loved. That there is a growth in complexity, and it's exponential, like in Moore's law, and that if you follow back the complexity of life as measured by DNA base pairs, what we find out is that it must have happened before the Earth formed, but not before the galaxy formed, or the universe formed. So it's a really interesting question that now astronomy and biology confront philosophy. Are we part of a cosmic ecology, and how can we see it? And that was the basis of the origin of this consortium that I'm a part of. ELF stands for the Exo Life Finder. A person of means came to me years ago here on Maui and said, well, what could you do if you started with a blank page and you tried to build an optical system that was just designed to find life in the universe? Now, I don't think Casey Harlington knew much about all the arguments I gave you, but he was generally interested in what could we do if we weren't bound by the directions and technology that Newton left us with. So the ELF consortium essentially started with the mantra: what optical instrument could we build over the next 10 years to find or survey for life on nearby exoplanets? And the argument for surveying for life on nearby exoplanets has grown over the years, because we've learned more about how many water-bearing planets are likely to be around other stars, and it's not an insignificant number. This was one of the first things that we looked at was, well, what would we have to do to make an image of an exoplanet? And this is sort of defining the optical path that we're going to have to take with telescopes. So if you imagine a star far away and an exoplanet that's symbolized in this drawing up here in the upper right, a telescope can't separate the light from continents. It would have to be many kilometers in size, and we're a long way from that. But it can separate the light of the exoplanet from the star, and we could integrate all of that light actually. And so what we showed was that if we measured the total amount of light that's reflected by an exoplanet that's orbiting around a star, and it's changing because of the surface features of the exoplanet, but it's also changing because of the orientation of the planet, that we get a light curve. And through what we call inversion techniques, we can find what the distribution of reflecting material on the planet is. And we can actually, so this is a simulation where we started with a simulated Earth, and we showed that if we had a certain amount of signal to noise in our reflected light, we could actually make out oceans and continents on exoplanets. So this is the image that guides our understanding of what it will take to make a picture of an exoplanet. And even more so, here's a satellite image of the Midwest, and you see these thermal spots. This is a thermal image. Those show that a signature of life is the heat that we produce. And the other part of what we showed in this argument a few years ago was that we could begin to make images of like this of exoplanets to show where life might exist because of the heat signature. The light has lots of information, and I see that I'm running late, so I'm going to accelerate the rate at which I'm talking about this. If it's of interest, come back to me at the end, and we'll answer questions. But the light, if you split it up by wavelength, means that we could also tell where forests and deserts and ice caps versus oceans would be. So what's the problem? Why haven't we done this already? It seems like it's straightforward. Well, the problem is, this is called the direct imaging problem in exoplanet research. And it's like looking beyond the glare of the headlights to see something which is much, much, much fainter than the faintest matchstick that might have been lit within a car. So this is a contrast problem. The glare of the star is so much brighter than the reflected light of the exoplanet. And this isn't important except to say that for an Earth around the sun, placed, say, at the distance of Proxima Centauri, it's the brightness of the reflected light off of the Earth is less than a billionth of the brightness of the star. And so that glare is an overwhelming noise source. The hard problem then is to make sure that the light of the star doesn't interfere with the light of the exoplanet. And that becomes two problems. One, as I showed you in the first slide, that we need to make a really big telescope. So that's called aperture. And to make a big telescope is limited by the effects of gravity, and that has to do with the mass of the mirror and how you make a support structure that is stiff enough to be able to create something that makes a good image. The other part of the problem is that light, if you think about it as a wave impinging on the Earth above the atmosphere, it's straight wavefronts that allow the light to be focused very precisely by a telescope. It goes through the atmosphere and then it becomes distorted. And so the wavefront distortion, either by the imperfections of the telescope or by the atmosphere, become the limiting problem in how we can concentrate the light to see this very faint exoplanet against the glare of a nearby star that's billions of times brighter. Okay, so here's some more technology having to do with light. So the wavefront is represented by this sort of granular scale that you see in these images. And what I've done is to compute how bright a star would look for a given amount of wavefront distortion when you go from 1 meter to 10 meters to 100 meters in size for the telescope. And this graph over here shows that, well, so in the first case, so think of this as a cut through an image where you had a bright star at the center, and you see that the graph goes up. That's the bright star, but the bright star is fairly broad. And again, that's because that's a small telescope. That's a 1 meter telescope. And out away from the star, there's still a lot of brightness. It's only, so on this scale, it's only a few thousand times fainter. Remember, we have a much larger contrast problem. As the telescope gets bigger, though, this wavefront problem gets less and less important. And when we get to 100 meters, without doing anything very heroic, on this plot, you can see that here's the bright star. The telescope has gotten bigger, so the image is narrower and more concentrated. And the diffuse brightness, where we'd have to find the exoplanet or the scattered light, is now almost 1 billion times fainter. So here's the wavefront problem. Here's how it improves when we get to a bigger telescope. All right, I wanted to show you what existing telescopes look like. And it's not very good for this problem. They're good for other things, but not this problem. This is a picture of the Keck telescope wavefront. So the Keck telescope, remember, has 36 mirrors and they're arranged in hexagonal pattern. The fact that this isn't a uniform color means that the wavefront is distorted. So the colors represent the distortion of the wavefront. And that distortion creates an image which should be all the light in a single point near the center. In fact, it isn't. All of those wavefront distortions make this image. Now imagine trying to find, and each one of those little, we call them speckles, is only about 100th to 1,000th as bright as the brightness of the star. Are we going to be able to see an exoplanet in this mess? And the answer is no, because the exoplanet is 1 billion times fainter than this, 10 to the 9, let's say. And that's the problem. That's the problem with the current technology. That's why the large telescopes that were being built have the potential for doing some of the exoplanet science, but they won't do very well with direct imaging. So there are other technical reasons for making a big telescope. It turns out that the time it takes to measure a certain signal gets smaller as the diameter of the telescope to the 4th power. That means if you double the size of a telescope, that the time it takes, instead of taking an hour to get to a certain signal to noise level on the exoplanet, it would take only 4 or 5 minutes. The intensity noise that I showed you before in that plot, so the background noise goes down like the square of the telescope diameter, and then finally the number of exoplanets that we're able to see increases like the diameter cubed. So everything is in our favor. If we wanted to build a telescope to, say, do a census of exoplanets, making images of their surfaces, the best thing we can do, well, we want to be able to decrease the noise in the wavefront. You can see that term here. But more importantly, we want to be able to make the telescope as big as we can make it. That's the key to solving this problem. And that's a hard problem because as we make telescopes bigger, we know that they get phenomenally expensive. So the 30-meter telescope, by some estimates, is $1.5 billion. The Keck telescopes were about $100 million. The mass and the cost of telescopes are proportional to the diameter squared. Now, there are some telescopes that don't follow the same scaling relation. For example, I showed you the image of the Green Bank telescope. It's 100 meters. That's only $0.2 billion. That's a number that some of us consider to be manageable, but it's not good for optical observing because it's not quite stiff enough. So what this ELF consortium has been doing is trying to develop technologies that allow us to get down to this cost scale for a 100-meter scale optical telescope. And those telescopes have variously been called the Exo Life Finder telescope at sort of 25 meters, or the Colossus telescope at close to 100 meters. And in both cases, the numbers are about a factor of 10 if we can make the technology that I'm going to show you in a minute work. So we said the two problems were wavefront control and aperture. We're really going to get into the weeds here for a minute, and I won't push these ideas except for those of you that worry about optics and interferometry. The approach to make a telescope this big, that is light and that also controls the wavefront, that we believe works, is to make it a series of independent telescopes, each one of which is this is a parabola, and each one has its own secondary mirror. And we combine the light at the very end, not like in the Keck telescope where the light is combined up at a secondary mirror from a bunch of different segments. So we want to make the segments as big as we can, and we want to combine the light at the end of the optical system in what is often called a physo-interferometer. We're not going to make mirrors like Newton made them. We can't afford to make them that big and thick and heavy because they will distort, and we can't create this large enough optical tracking structure to satisfy the wavefront requirements. So the idea is to make the glass a couple millimeters thick. When the glass is thin enough, the shape of the glass is determined by the surface tension of the material on the two sides of the glass. So it's almost like water. The surface tension in water makes a very flat surface. Glass is sort of liquid, not really, but it has some of those properties. And the surface tension on the two sides, when they balance, make a flat piece of glass. Now, if you could change the surface tension on one side of the glass, you would create a curvature. It wouldn't be a change in the height of the glass except through the curvature change. And what we've done is to show that by using a high-powered laser at 10 microns, the light isn't absorbed through the glass, but that heat changes the local curvature, and we can create a curved, locally curved piece of glass by changing the heat, or there are other methods for doing it also. So if we can measure a piece of glass and it has deformations due to the manufacturing process. Take a window, for example. You know that you can see the distortions in the window. On very small scales, the window is very smooth. And we'll map that, and then we'll use this technology to polish the glass through what we call curvature polishing. And it's all done by computer on a gantry. So what it does is it allows us, so this is a conventional mirror. These are small, of course, but this is a conventional, and that's actually has a parabolic shape. Its thickness to diameter ratio is about 1:8, and that's required to be stiff enough. This is one of these curvature polish mirrors, and there it is, 2 millimeters. And these are just some of the intermediate steps that are used to help generate that curvature. And so we've gotten to the point where we're not building 5-meter mirrors, which is what we want to be able to have for these segments, but we're building mirrors that are about 5 inches. And our first step in this process is using these high-powered lasers to do this. So the other part is the wavefront control, and this is a technical figure, but it shows this again, this idea of an odd number of mirror segments arranged in a ring in what was that, I called it a physo-interferometer. If the wave that strikes the mirror is delayed or advanced from each one of these by a constant amount, we can correct for the atmosphere. And this is like that first slide I showed. This is the concentration of the light, and the concentration of the light is affected by the color here represent what we call the phase of each one of the mirrors. The image, therefore, the image encodes the information about the placement of the mirrors. We say that the piston phase of each of the mirrors is recorded in this image if we only knew how to go backwards, take an image, and then turn it into a measurement of the phase. Similarly, the tilt of each of the mirrors for a small tilt, and that's represented by, see the color gradient on each of these, the tilt also affects the images in a different way. And these are for different wavelengths. And this is just the position of the mirror, and this is the tilt of the mirror. So one of the key technologies that you've heard a lot about over the recent years is machine learning. And what we've shown is that we can take an image of a star, and without doing anything more than training a neural network, we can extract the information to correct the phase and the tilt of each of the mirrors. So that's a key ingredient in the new technology to make mirrors work. This is just an illustration of what the atmosphere does. And this on the lower panel represents the image that you see. And I'm going to show you a movie here that now shows how, as the degree of turbulence of the atmosphere decreases, we're able to pinpoint the light and localize it. So when the atmosphere is very turbulent, that corresponds to the small number you see here. The colors on the mirror represent the distortion in the wavefront that's residual. We don't really get much of an image. And what you'll see as this movie progresses is the effects of the atmosphere for two different assumptions about what the mirrors do. You begin to see there's a point-like brightness appearing here. So the atmosphere is getting more stable as we go. The image residuals are still very chaotic, as expected. We can't see an image here, but in our wave, so on the right is what our machine learning solution does. And now you're beginning to see that actually the airy rings are visible. The light is being concentrated as much as we can with this kind of mirror. So this movie is meant to show you that the technology for doing wavefront correction has advanced quite a bit with this new idea that neural networks can encode different ways of solving, in this case, numerical problems. So that's another piece of the technology that we need to make this telescope work. The third is that you see that here's the footprint again of this new telescope called ELF. And here's the brightness, and you see that there are lots of rings, the stars at the center. It's still going to be hard to see an exoplanet because of all of that scattered light, in this case, diffracted light. Well, the other thing that is possible now that we're building a telescope, which is really an interferometer, is we can put on each of the mirror segments, we can add a phase, and that phase means that we can construct, we say we can synthesize a diffraction pattern that is advantageous to finding a dark spot in the presence of all that starlight. And here's how that works. So put these phases on each of the mirrors. Here's the phase distribution. And look what happens in the diffraction pattern. We can create a diffraction pattern that now has a dark hole. We can put that dark hole wherever we want it. But if there was an exoplanet at a billionth of the brightness of the star, well, we can't quite get to a billionth, but we have other tricks for doing that. If there was an exoplanet there, we can see it against the glare of the telescope system that is diffracting. That's the other critical piece of the technology to solve this problem, is build a telescope which is intrinsically designed to control where the light goes and keep it from interfering with the exoplanet. The last fundamental change is, as I said, is that a telescope is an optical and a mechanical system to link together. You might have heard the term tensegrity. Buckminster Fuller was one of the first ones to mention it, and it's this idea that if you build a structure from, and it's inspired by biology, our bodies actually have a very low mass compared to the stiffness and strength that we have, and it's because we have tendons that connect the bones in joints, and that the tendons are in compression to create the compression of the bones. The bones are never extended because they're much weaker that way. The idea is this: imagine that you had say a truss, that's this vertical object here on the left, it's pretty obvious, right, that if you had the same amount of force pushing down on that truss, the truss wouldn't distort very much. But if you pushed from the side, the truss stiffness is much less and it would distort. So if you want to build a structure that is very stiff for the minimal amount of mass, build it so none of the trusses have any kind of, we call this a shear stress. They don't, by the nature of their design, they don't allow any forces to operate perpendicular to the axis of the stiff elements. Well, there are biological examples that are pretty remarkable. One of them is a spider web. If you look at the microscopic structure of the polymers in a spider web, it consists of the stiff, called pleated sheets. Those are like the bones, and then amorphous chain molecules that connect them. And you might be interested to know that a spider web, remember, it's the ratio of the stiffness. We call that the Young's modulus to the density. A spider web has a specific stiffness which is greater than steel. It has a very low density, which is why we don't think of it as being terribly stiff, but that low density admits this enormous strength. A tensegrity structure, which we can build now, consists of rods and strings. And if the strings pass over the ends of the rods, then by the nature of that structure, it must be tensegrity. It will create something that is overall stiff for a minimal amount of mass. Okay, I'm almost done. So the consortium, which is now in the throes of building a prototype of this sort of optical telescope, is based on French and Spanish and German scientists with some from the Institute for Astronomy. The telescope looks like this. This is a prototype which is not 25 meters across, but about 4 meters across, 16 feet. These are the tensegrity elements. They're cables that are linked, unfortunately not by slip joints, but in this first step, we're creating a tensegrity structure, which is like a bicycle wheel. A bicycle wheel is an example of a structure which is incredibly stiff when you place it on the ground, as bicycle wheels roll. The spokes are in tension and the wheel elements are in compression, and it's very stiff for the mass that it has. And that's the structure in this telescope that's at work. Here's a better picture of it. This shows the light path. Each one of the primary segments will be one of these curvature polish mirrors, and the light comes together in a final focus, which is down here in the base of the telescope. The European Union has come up with some money to put together a research group to try to put these ideas into the next generation of large telescopes. It's called the Laboratory for Innovation in Optomechanics. And this just happened a couple of months ago. We're in the process of developing what we hope is a center where these ideas can not only be prototyped, but be available to build the next large 50-meter optical telescope for this problem. Ultimately, we hope to be able to support a program called the Breakthrough Foundation. The Breakthrough Foundation is interested in sending a probe to the nearest exoplanets at not chemical propulsion speeds, but relativistic speeds. So there's a group of scientists that is prepared to try and use 100 gigawatt lasers to propel a 1 gram nanocraft to the vicinity of Proxima Centauri. And the optical telescope could look something like this that could do it. So we're believing that not over the last 400 years, but over the next 20 years, that there are technology prospects that are going to change our vision of the universe, and perhaps how life in the universe came about and how it might advance. And I see that I'm late, so I'm not going to read this list, but this is a summary of the ideas that we put together here for this telescope system and for LEO. So with that, I will quit and try and answer your questions.
Thanks very much, Jeff. That was really interesting talk, and we appreciate you speaking with us today. The floor is open for questions from the audience, so feel free to either just unmute your microphone and speak, or you can raise your hand with the reaction button and we'll come to you, or put something in the chat box. I'm going to start off with a question then, might be naive, but you were mentioning distortion on mirrored glass as being an issue as the telescopes are increasing in size. Is that due to just bending of the glass because there's a lack of physical support as it becomes a larger and larger structure, or is that issues that have to do with the flow of glass over time when it acts a bit like a liquid and distorts in that way?
Yeah, that's a good question. The glass distorts over, it flows, as you point out, over very long time scales compared to what we worry about. Our concern is just the gravitational deformation. Like any object supported from 2 points, gravity will deform the object, and that's what we have to fight against. We have to be able to make those deformations smaller than the wavelength of light in order to create the concentration of energy that lets us see the exoplanet symbols. So the glass deformation problem is one, just the mechanical deformation. And something I didn't mention, which is part of the answer to the problem, is that in existing design telescopes like the Keck, there are electromagnetic sensors that push and pull on the edges of the glass to make them line up properly. In the mirrors that we propose, because they're so thin, we can put a thin layer of what's called an electroactive polymer on the back surface, and when we put a voltage on it, the polymer shrinks or expands, and we can use that to counterbalance gravity. So in a way, older telescopes created stiffness by having lots of mass in glass. And what we want to do is we want to create stiffness by using the electrostatic energy in electroactive polymers. And so that will be our approach to stiffening the glass as it deforms.
Okay, we have KN with a raised hand. Please go ahead if you want to unmute.
I think I took Astronomy 101 like a long time ago with you, but
Okay.
yeah, I live in the Midwest now, but I was watching your talk with my son, and we had some questions for you. And for example, there's 3 questions. One is like, is glass the only material that's appropriate to make these telescopes, like these giant ones?
Okay, let's hit that question. So if you have $10 billion for a small telescope, say 6 meters, there is one material which has an advantage over glass, and it's called beryllium. Beryllium is a very lightweight element. It's a metal. It can be polished to be highly reflective, but it's very toxic and very expensive. And what it does is, so this ratio of stiffness to density matters. If you can make something very stiff if you make it very heavy, but if you make it very heavy, then the gravitational deformation you lose because of that. So beryllium is relatively light and relatively stiff. So it has a stiffness to density ratio that's about 8 or 9 times better than glass, and that's why the JWST was made that way. But we wouldn't do that on the ground because it's not such a big advantage, and because the difference in the cost compared to glass is a factor of almost 1,000 when you work it out.
Wow.
And so it turns out glass is a remarkable material. It, as I said, it has basically the same stiffness as steel, and it's incredibly cheap. Glass is one of the least expensive building materials on the Earth, and of course that's in part because silicon dioxide is in sand is so common. So we looked at that question you asked, is glass the best thing to use? And it doesn't take long to convince yourself that it really has many advantages.
Mhm.
Sorry, what was your second question?
Okay. Second one is, can we use our own like sun and earth for a model for the machine learning? You know how you said that we can like use the computer to like make it learn how to focus on the light the wavelength. So maybe we can simulate it using our own solar system by putting somewhere, and I don't know, something in within like closer. I don't know if it's possible right now, but maybe in the future, like put some telescope out there and then see how it is, and then using that data, maybe we can use it also towards like the further galaxies.
Yeah, I think that's a good idea. So what you're saying is that we don't really know how to look for what the signatures of life might be.
Yeah.
And so let's train our machine to understand life by looking at the solar system. Now the problem is, right? The problem is there's only one training set. That's the Earth.
Yeah.
Right? So machine learning, unless it's unsupervised learning or uses other techniques, I'm not sure how you would train it to recognize life. I think what we know is that if we saw evidence of deserts and we saw dark regions where where starlight was being converted into energy, we could deduce that. So the neural network that's in our head might be for a while the best solution to understanding the data that comes out of an ELF telescope. The neural network that we were using uses the starlight to help us fix the mirror distortions. And that's just, the star is just a source of photons and energy. There's nothing very special about that. And the neural network is just there to train how the speckly image of the star contains the information to correct the shape of the mirror and the optics. So that's a more standard application of a neural network in machine learning. The one of finding life, I agree, is very hard, and we're going to have to use all of the tricks that we know to be able to find it. I think our goal was to start by looking for images of exoplanets around other stars, and then let's see where we go from there. Maybe our own biological neural net will help us solve that problem.
Oh, nice. Can I also ask the third question?
Sure.
Okay. Can we, for example, in the future, make a telescope on the moon? Because on the moon, it would probably have less problem with that gravity issue, and there's no atmosphere, and it's close enough to maybe transmit the data to people on Earth.
You should be an astronomer. I'm all for that.
Actually, this idea came from my 11-year-old son.
well, make sure he keeps working in that direction. The answer is we would love to put this telescope on the moon, and we're trying to convince Yuri Milner, who is the head of the Breakthrough Foundation, that he should invest with Bezos in creating the infrastructure that allows this. Because, as you say, the fact that, I mean, there's another benefit, which is the moon rotates very slowly compared to the Earth, and so the tracking requirements get easier. The gravity is less, so that gets better. The absence of an atmosphere means that we don't have to worry about atmospheric distortion. The amplitude of the gravity is less, so the overall gravitational distortion is less, and the material is less. The kind of things that we worry about are, there's dust that's lofted into the lunar environment, and we'd have to learn how to deal with correcting for or cleaning mirrors of what is probably pretty nasty lunar dust. But I would gladly trade that problem for all the other technical problems that we talk about. So yes, I think that the right place to do this problem is from the moon, if we can solve the cost problems and the infrastructure problems there.
Nice. Thank you.
You're welcome.
Thanks for those great questions, KN's 11-year-old son. That's fantastic. We have a question in the chat from Joan. So other than the problem of deploying such a large telescope to space, what are the obstacles that make ground-based the only option?
Yeah. So NASA will deploy LUVOIR, which is in one configuration, it could be a 15-meter telescope, still much smaller than this, but it's 25 or 30 years away, and the cost. So remember the 6.5-meter James Webb telescope, which is a 6.5-meter telescope, a segmented telescope with all of those problems, was $10 billion. So there's a multiplier to go to space, which is between 100 and 1,000 times what it is to do on the ground. Since we don't have to solve the transmission of light problem through the atmosphere, we can work in the visible and the infrared bands where the atmosphere is transparent. We think that the ground is where this will happen. NASA has several plans to do exoplanet science, and we're all cheering that on, but it tends to be expensive. The scale of the financial investment we're talking about for, say, a 25-meter, 30-meter telescope like the ELF is about $100 to $150 million. Compare that to $10 billion for JWST. That's the numbers. Those are the numbers you have to overcome to go to space.
That makes sense. Well, I think at this point we should probably wrap up because our time is moving on. So we'll end our Q&A session here. I'd like to extend a final thank you to Jeff for your webinar presentation today. That was really interesting. And also thank you all for attending. We'll look forward to seeing everybody soon. Thanks again, Jeff. Our next event is going to be held on Wednesday, October 26th at 2 p.m. Hawaiian time. It's going to feature Mark Hickson. He was our inaugural Pilina speaker when we first began this webinar series about 1.5 years ago. He's a faculty member of the School of Life Sciences, and he's going to be speaking on a topic entitled Saving Hawaii's Coral Reefs. Scientists can't do it alone. So watch your inboxes for invitations to that event.
Great.
And thanks again, everybody. We hope you have a wonderful rest of your day or your evening. Aloha.